All right, welcome back everybody. We're now in the 14th week of class. So we're getting pretty far along and getting close to the end. This week, things are going to work a little bit differently than usual. I've already announced this and sent a few emails out about this, but just to remind you, today for this lecture is the only time we're meeting in person this week. We don't have any labs this week. And Wednesday, there aren't any classes campus-wide actually. It's something called Faculty Lecture Day going on. However, I am going to record a lecture after this one that I'm going to expect you guys to watch. It's going to be relevant for the homework that I give you. By the way, that homework assignment, homework 14, is up there on the board. So you're actually going to be responsible for watching this video. Okay? We've done this once before. Hopefully this is the only other time we're going to have to do this. But again, there is some material we need to get through in order to stay on track. Okay? But again, there is no lab. However, has anyone checked Canvas? I made an announcement today about a possible extra credit opportunity. So basically, I have a virtual lab that you can do. It's totally optional. You don't need to do this. But if you do it, you can get up to 15 points of extra credit. So check Canvas for the details of how that goes if you're interested in the extra credit. Okay? Go ahead.
Are those 15 points only added? Are going to be added to the lab or to the class?
To the lab. Yeah. So it's your lab total. Okay. So not quite as valuable as a lab, but close to it. All right. Anything else? And then just one other thing. Of course, we're about 2 weeks away from our third test. Okay. So the lecture that we're on right now is sources of magnetic fields. We're going to get through some of that here today. And we're going to finish it up in the lecture recording that you're going to be responsible for seeing later this week, okay? So actually, my plan is to give you this lecture and then just record the rest of it, like right after. So that'll be up sometime later this evening, okay? Any questions on that? All right, so let's get into it. Let's start with this, because this is where we left off. Remember, we were talking about Ampere's law, so when you think about this question, you should be thinking about Ampere's law. This is something called a coaxial cable. It's something that you use all the time in your household for internet and television connections. And it basically consists of a conductor. Let's call that radius A on the inside. And then we have sort of a cylindrical shell on the outside, where the inner radius of that shell is B. So from the center to the inside of this shell is B, and then the outer radius is C, okay? In between the two conductors, you have some kind of insulating material so that they can be separated. And the way a coaxial cable works is both of these conductors carry a current, but in opposite directions. So basically, one of them is carrying a current to your device, and the other is carrying the return current back into the wall, essentially. So what you want to imagine is we have current I flowing along the inner conductor, and then an identical amount of current flowing in the outer conductor, okay? So I have two questions for you. First is, what is the magnetic field at the very center of this wire, right here at R equals 0? And then what is the magnetic field outside of the wire where your radius is greater than C, okay? So this shouldn't actually take too much calculation if you think about it carefully. So take a few minutes, see what you come up with, and then we'll go through it together. Again, think back to Ampere's law as far as how you want to approach this. Particularly, think about how much current you're enclosing in each of these two cases. What about the outside? Looks like you got it, Hazel. Okay, I'm seeing a few people have gotten this. And again, this shouldn't take much calculation at all because, well, you guys tell me, what's the magnetic field at the very, very center? Zero. What is it outside of the wire?
I. Zero.
It's also zero. Zero in both cases. And in particular, that second case of being outside the wire and having zero B field is really important to how the coaxial cable actually works. It's designed that way. In other words, it's designed to sort of shield the outside from any stray magnetic fields it might be producing that can interfere with other electronics, okay? So let's think about it this way, okay? We have B dot dl equaling mu naught times I enclosed. And in this sort of situation, the geometry we're dealing with, if we're like looking down the barrel of the wire, is like this. We choose a path that basically goes in a circle and loops around the wire like this. And we call the radius of that Amporian loop R, okay? So of course, if R is equal to 0, we're not enclosing anything, right? Because our path has 0 area to it, so it has nothing to enclose, right? So in that case, I enclosed is 0, and that immediately implies that B equals 0, okay? But if R is greater than C, we have a similar kind of situation where the enclosed current is now the total current enclosed in both of the conductors, right? So one of them is carrying a current I going in one direction, the other is carrying a current I going in the opposite direction, and we're enclosing both of those. So you might want to think of that as plus I and minus I being added together for the opposite directions, giving us 0 enclosed current and 0 B field. So again, the B field is basically 0 everywhere outside of the cable, and again, that's how it sort of shields itself from interfering with other electronic devices. Okay? Any questions about that? Let's do another example. We're still doing Ampere's law, by the way, and we're still dealing with wires. We're going to move on after this one to other types of geometry, but let's deal with this one last example before we move on. So here we have an infinitely long conducting wire of radius r. So remember, capital R, that's the radius of the wire itself from the center to the edge. Now, we did an example last week like this where there's a uniform current density in the wire. Now, let's do a non-uniform current density. So this is kind of similar to when we dealt with Gauss's law and we had non-uniform charge densities, right? So in this case, the current density as a function of radius is given by this function right here. J, that's your current density, equals J naught, times little r, that's where you're located in the wire, divided by big R, okay? So what we're going to do is use Ampere's law to find the magnetic field as a function of distance, okay, distance from the center. So this should look familiar. We did one like this before. Just to remind you, we're going to split this problem up into 2 parts. First, we're going to find an expression that's valid while we're inside of the wire, okay? So for that one, we're going to use Ampere's law and apply it to this loop, where the radius of the loop is less than the radius of the wire, indicating that we're on the inside of it. And then you can probably guess what happens next is we do it on on the outside. Okay, so we'll do a loop that's outside the wire and see what we get there. Okay, so that's the plan. Let's work it out for the first loop. Okay, so here we go. This is loop number 1, where little r is less than big R, indicating that we're inside the wire. And remember, what we're trying to do is evaluate B dot dl equals mu naught times I enclosed. So we not only need to evaluate the integral B dot dl, but we also need to find the current that we're enclosing with this loop, okay? So let's do that first part, the B dot dl part. If you remember from last time, in a situation like this, the B field is going to form circular loops around the center of the wire like this. So the solid line here represents our B field, okay? And then this dashed line I'm going to use to represent our Amporian loop. So remember, what we do when we evaluate the integral B dot dl is we evaluate it around this entire loop, okay? So, remember how this goes? We have a dot product, so we have the integral of B, the magnitude of that vector times the magnitude of this vector dl. And I've chosen things so that dl and B, they're both just going in a circle, pointing in the same exact direction at each point. So 0 degrees between them. If you remember what happens next, cosine 0 becomes 1. B is something we can pull out, because if you remember, B only depends on your distance from the center. If we're staying the same distance away from the center the whole time, B is a constant for our path. So we pull it out. And then we have the integral of dl as all that's left on the inside. And so what that is effectively is the total length of the path, right? What is that again? That's 2 pi r, yeah? The total distance around the circle is 2 pi r, okay? And it's pretty much always going to work that way when you're dealing with this type of geometry, okay? Now let's work out the current enclosed part. Okay, so for this, we're going to have to remember what the definition of current density J is, okay? J is, I'll just write it in words, current per area going through a cross-section of the wire, okay? But the thing is, it's not uniform. So what we can't do is just assume that J takes on the same value everywhere. Instead, it's changing. In particular, it's getting bigger as R increases, okay? So I'm going to have to write this in differential form as di, some infinitesimal amount of current, divided by dA, some infinitesimal amount of area, okay? And what I can then do is rearrange that to say di is equal to J times dA. All right? And then what this is suggesting is we should probably integrate both sides, because if I integrate over all my little elements of current di, and I include every little bit that I'm enclosing, then that's exactly what I'm trying to calculate, right? I enclosed. But, okay, this has 2 parts to it. J, of course, is what we were given. That's J naught times little r divided by big R, like this, okay? What should I put in for dA? Think about that.
Pi r.
Yeah. For dA, I'm just going to work this out on the side, because we have a circular area, right? Pi times r squared. If I take the derivative of that with respect to r, that takes the 2 out front and reduces the power to 1. And then if I just solve for dA instead of dA divided by dr, dA becomes 2 pi times r times dr. Okay, so that's an infinitesimal element of area that I'm going to be integrating over here, okay? But let's get some kind of intuition for this. The intuition is like this. The area can be thought of as a little ring, a really thin ring, where the radius is r, and the thickness of the ring is dr. And basically, if I take 2 pi r, that's like the length all the way around, times the thickness, which is dr, that gives me this area, okay? So that's where it comes from. Of course, you can just work it out like this, but that's some intuition, okay? So now we have everything we need to express di, and we'll remember that I enclosed is just the integral over di, okay? So that's integral of j dA, and now I'm going to plug in for each one of those. J is j naught times little r over big R. That's our non-uniform current density. And then dA is 2 pi r dr. All right? So just looking at this integral, before we try to evaluate, why don't we just pull out some constants? What do I have that can be pulled out? 2 pi.
J naught, big R.
Yeah, all that. So I have 2 pi j naught divided by big R as constants. And then I have little r squared times dr. And now I have to put the limits, okay? So let's be real careful about this. The idea here is I'm trying to figure out how much current I'm enclosing with my Amporian loop. So how do I figure that out? I go from 0, from the very center, all the way out to the radius of this Amporian loop, okay? That's 0 to small r, actually, right? I'm not including the entire wire, right? I'm just including some part of it, which has radius small r. So to avoid confusion, sometimes what we do is we put a little prime on the variable in the integral. This is called like a dummy variable, so that it won't be confused with that radius over there, okay? So, I mean, basically the integral is just a power rule, right? We have something squared. So what happens when we integrate something squared? 1/3 times, yeah, 1/3 times r cubed. So here we have 2 pi j naught divided by big R. And then we're taking 1/3, I'll write that as r prime cubed, going from 0 to big R like that, okay? So, I mean, of course, when we plug in the bottom limit, you're just going to get 0. So hopefully you can see that overall, it's 2 pi times j naught. Then we have 3 times big R on the bottom. And then it looks like on the top, we have small r cubed. Okay, so this would tell me how much current I'm enclosing if I go out to this particular radius right here. Okay, that's what this means. So any questions up to this point? Yeah, Devontae?
What was that? That's not an N, that's a R?
Where? Here?
Or yeah.
Oh yeah, yeah, so I'm just putting a little prime on it. You don't actually have to do this, but sometimes, like, I want to distinguish between what's on my limits and what's the function in the integral. It doesn't really make a difference, it's a notation thing, but I just put a little prime there, yeah.
When I was doing this, I tried to read this, I was stuck on when we put J equal current divided by area. How can we derive that when you say, for example, the area is pi r squared? You can find dA equal, what about J?
So here's what we did, right? We said di, so on this step, we said di is j times dA.
Yeah.
It's non-uniform, so we're just using the function we were given. That's what we're, so you have to be given some kind of function if it's non-uniform. Remember, thinking back to Gauss's law days, right? When we had non-uniform charge density, like rho as a function of r, we'd have to plug in that particular function in order to evaluate. So it's like that.
Yeah, let's say you put J equal I divided by A and derive it. How are we going to jump from Ji equal JDA?
So the problem with doing that is, again, it's okay to just say I divided by A if J is uniform and it just has one value. But if it does not, if it changes with distance, then we have to use the differential form. That's why. Yeah. All right. So yeah, it's a little tricky, but remember, we've seen things like this in the past to try to make that connection. All right, so here what we have is I enclosed and B dot dl. So the work is basically done because in Ampere's law we have integral B dot dl equaling mu naught times I enclosed. So let's just plug in what we know. B dot dl integrated over our loop came out to B times 2 pi r, just r like this. And then on the other side, we have mu naught times this whole thing, which is 2 pi j naught r to the third divided by 3 big R like this. And yeah, I think that's everything. So we can cancel some things out like 2 pi. And of course, if I divide out the little r, I'm just going to have little r squared here. So overall, B is equal to mu naught times j naught times little r squared divided by 3 times big R. And that's our expression. So what it's telling you is that our B field is growing in intensity like R squared as you go from the center of the wire and go outwards. But of course, this is only valid if we're on the interior of the wire. Okay, as soon as we go outside the wire, there's a whole nother analysis to do, okay? So that's the first result. So going back to the slide real quick, that's our first result for the magnitude of B when we're inside the wire. So now, to get it when we're outside the wire, which by the way is going to be a lot easier to do, what we're going to do is take this second loop, which looks the same in terms of its geometry, but it's just a bigger loop, and it encloses the entire wire. Okay? So in other words, we know what the B dot dl expression is going to look like. It's just the same as before. But when it comes to the I enclosed part, we're now just enclosing all of the current within that wire. Okay? We're just enclosing the whole thing. So let's just work that expression out, and then we'll have our answer. So now, if we look at loop number 2, which has the radius of our loop bigger than the radius of the wire, which means we're outside, I'll write it this way. I enclosed is the same as I total. It's the total current running in the wire. So if I go back to my expression from before, the one with the check mark right here, okay? What would I change about this expression if we're just outside of the wire and enclosing the entire thing? What would I do differently here? Yeah, so I would go in my integral not out to little r, but out to big R. If I go out to big R, that means I'm enclosing all of the current within the wire. That's what it means to do that. So if you follow along, I'm going to take this expression here and just plug in big R. 2 pi j naught. Big R cubed is what goes here now, divided by 3 times big R. So to consolidate this a little bit, it's 2 pi j naught divided by big R squared, right? Because we have some cancellation here. And then divide by 3. Okay? So we can use a lot of the work we've already done. And then we apply Ampere's law, which is integral B dot dl equals mu naught times I enclosed. So the B dot dl part is just like before. It's the magnitude of the B field times 2 pi little r. And then we have mu naught times 2 pi times j naught times big R squared divided by 3. So what is this telling us overall? the B field, after canceling out the 2 pi here, and then dividing out the small r and putting it on the bottom here, we have u naught times j naught times big R squared divided by 3 times little r. And that's our result that we wanted to get to. So again, it's kind of right here in the bottom corner. And notice, how does our B field depend on small r? How does it depend on our distance from the center of the wire? Well, now it's decreasing as we get further out, okay? With a 1 over r type dependence, okay? So we good on that? Okay. So to summarize that part, after applying the Ampere's law to that second loop, we got this, u naught j naught, big R squared divided by 3 little r. But we could also write this as just u naught times I total, right, divided by 2 pi little r. These are equivalent expressions, okay? In one case, we're just going to write I total, and in the other case, we're going to express it in terms of the function we're given, okay? So they're equivalent to one another.
What does J naught, like, what does that represent though?
It represents, in this function, the maximum amount of current density you get. So here, if you try this, try plugging in 0. That's telling us that at the center, we have 0 current density. If you plug in big R, then this just becomes J naught, right? So basically your current density is 0 in the center, and it grows, and the biggest current density you get is right on the edge of the wire, in which case it's J naught. That's what it is doing in this formula, okay? All right. And basically, yes, once you're on the outside, it just behaves like the thin wire expression we worked out before. So as a little bit of a summary, just note what this would look like if we were to plot it out, okay? We have these 2 expressions, and what we want to understand is how it would look like if we graphed B, the magnitude of our B field going vertically, versus distance from the center, which is lowercase r, okay? So we have a whole bunch of constants floating around, of course, but how does it depend on little r? Well, when we're on the inside, remember, it's r squared. So this should look like a parabola going concave up until we hit the edge of the wire. Okay, after that, it's 1 over r sort of dependence, and we know that this looks like a curve which is decreasing with distance, all right? So what's happening is your B field is 0 right in the middle of the wire, gets stronger and stronger as you reach the edge of the wire, but then once you start to go outside of the wire, it falls off again. So that's what it looks like when you graph it, okay? Any questions on that? Oh, no question? Okay. All right, so we spent a lot of time on wires and how to apply Ampere's law to a wire, just a straight wire that is. Now we're going to look at some of those other types of geometry that I told you about. In particular, solenoids is what we'll start with, okay? So let me tell you about what a solenoid is to start. I mean, a solenoid is pretty simple. It's just take a cylinder and then wrap a wire around that cylinder many, many times. Run some current through that wire, and then you've got a solenoid, okay? So let's try to understand, like, just visually what the B field due to a solenoid looks like, okay? So let's imagine that this is our wire. It's kind of spiraling along the cylinder like this. And we run some current, so we have current going in this way, and then current going out through the other end, okay? So remember how B fields work, just generally speaking, right? B fields will form loops around whatever wire segment you have, okay? And that's certainly true for the solenoid, right? In other words, like, just take a look at this little segment of wire right there for illustration. What we have is a B field line which loops around that, okay? And if you look at any other segment of the wire throughout the solenoid, it's the same deal. The B field is kind of looping around that segment, okay? But here's the thing. The B field lines are going to be much more tightly packed on the inside of the solenoid compared to the outside, okay? Because basically, if a B field line loops around, right, you're going to have exactly one line that's on the inside and one line corresponding to that on the outside, right? But typically a solenoid is going to be pretty narrow, so it's going to have a pretty small diameter, and it's going to be pretty long, okay? So all of these lines that are on the outside are spread out throughout a huge volume, right? Whereas the ones that are on the inside are packed into a tiny little volume, okay? So what does that tell us? The more tightly packed the B field lines are, the stronger the B field is, right? So you have a very, very strong B field on the inside, and then a relatively weak B field on the outside, okay? And in the limit where we take the length of our solenoid to go to infinity, actually, it becomes 0 B field on the outside, and a very strong and perfectly uniform B field on the inside. What I mean by uniform is, you can kind of see here, but if you're on the inside, all the B field lines are going in the same direction, right? Okay, so from here on out, when we analyze solenoids, we'll act as if the B field is effectively 0 on the outside. It'll be small enough for practical purposes to treat it as if it's 0 on the outside. And on the inside, it's totally uniform. All the lines just go along the axis of the solenoid, and that's it, okay? So we all clear on the basic picture here? So now what I'll show you is how to take that picture and apply Ampere's law to a solenoid, okay? So let's be clear on what this picture is showing you, because it does become hard to sort of represent this stuff on a two-dimensional sheet or a piece of paper, right? So what you're looking at here is a cross-section of the solenoid. Okay, so let's imagine this is the cylinder, got a wire wrapped around it many, many times, and let's say the current is flowing this way, okay? So let's take a little cut of the solenoid, like if I just to cut it right here, and you were just to take a look at that cross-section. So basically all the wire segments on the top would have current going this way, and then all of the wire segments on the bottom, the current would be going the other way. So that's what you'd be seeing. And then in terms of your B field lines, again, they'd just be going across the solenoid and be relatively uniform, okay? So that's what the picture is. You're seeing on the top of that cross-section, current's coming out. We have a whole bunch of different wire segments, of course, because it's wrapped many, many times. We have a B field uniformly going straight across. And then on the bottom, we have those same wire segments, but since they're wrapped around, the currents are now going into the page, okay? So everyone clear on the picture? All right, cool. Something that we're gonna use coming up is this, lowercase n, okay? It characterizes how tightly wound the wire is, okay? What it means is the number of turns of wire per unit length, okay? So lowercase n is the number of wrappings or turns of wire per unit length. So its definition is capital N, that's how many total wrappings you have on the whole solenoid, divided by L, which is the length of the whole solenoid, all right? So it's just number of turns divided by length. Right, and of course the current is going to be the same because it's just that same piece of wire wrapped many, many times. It's just a uniform current throughout. So that's going to be called I. We're going to come up with a formula for that B field in terms of these variables here, okay? So we good on that? All right, so the thing here is we have to use Ampere's law. We have to choose an Amporian loop. It's actually tricky to choose the right one, so I'm going to just show you how this works. Right? This is an Amporian loop that will give you the right answer. So our Amporian loop goes like this. It's basically a rectangle with 4 sides, and the first side is inside of the solenoid. Okay? So if we follow this part of the path, it's just going right along with the B field inside of the solenoid, okay? Follow the second part, it goes perpendicular to the B field, and then it just goes outside of the solenoid, okay? The third part is fully outside of the solenoid, but it's going in the opposite direction as 1. And then the fourth part meets back up where we started, so it's going perpendicular to the B field and then going back inside the solenoid, okay? So let me ask you this, everybody, right? Ampere's law involves B dot dl integrated over this entire loop. It's pretty straightforward that we want to break this into those 4 pieces, right? We'd want to evaluate for path number 1, 2, 3, and 4 all separately, right? Can anyone see where that integral is going to go to 0 for any part of that path? There's more than one, but can you see any? So that, it's not going to go to 0 for number 1, right? Because we are following the B field lines here. So 2, why would it, yeah, you're right. Why would it go to 0 for 2? Because we're perpendicular to the B field. So when you do B dot dl, the dot product ends up giving you 0. And that's the same over here, right? What about this part?
They just turn negative, right? If I'm not mistaken.
It's just 0 because there is no B field here. If the B field is equal to 0 and you're integrating over that part of space, you're guaranteed to get 0, right? So it's really only this top part where there's any kind of contribution, okay? So let's work it out on paper in some more detail. All right, so here we go. I'm going to just copy down that basic sketch where we have current going into the page like this. And we have our path, which is rectangular. And I'm labeling these as 1 up here, 2, 3, and 4, right? And then we have our B field lines only in this region going straight across, okay? So here we go. The integral over the loop of B dot dl is the integral B dot dl for path number 1, okay, plus the integral B dot dl for path number 2, and then the integral B dot dl for path number 3, and then the same for path number 4, right? All right, so again, it has to overall be a closed loop for this to work, so we have a closed loop. All right, so for number 2, that's going to 0. Why? I'll write the answer up here. B is basically just perpendicular to dl. Okay, so if you dot 2 vectors that are at 90 degrees to one another, one's going straight down, the other goes straight across, you're guaranteed to get 0, okay? For B dot dl3, that's just 0 because B is equal to 0, right? There is no B field out here, okay? And then for B dot dl4, it's 0 for the same reason as for number 2, because B is perpendicular to your path. All right, so it's only number 1 that remains. Here's how we analyze it. So for the integral over the entire loop of B dot dl, it's only the first part of that path that contributes anything, only the part that's in the solenoid, okay? And let's work it out. So we have a dot product, right? That's B dl, I'll call it dl1. And then we have cosine of the angle between my path and my B field. What's that angle? 0, right? You're going exactly with the B field for this part of the path. Also, here's the next step we take. B is uniform, at least inside the solenoid. So we could pull it out. B is not changing, it's just a uniform value, so just pull it out. And then we have integral dl1. Okay. So of course, when we integrate that, we just get the total length of path number 1 that you see up there. But this is not a circle or anything like that. The geometry is totally different from before. So what I'm going to do is just call this generically L. Okay? So just the total length of that part. Let's just call it L. And then we just have B times L. Okay? On the other side of the equation for Ampere's law, we have I enclosed. Now for this part, you want to be a little careful. You might be tempted to say, well, if the current running through the wire is I, then I'm just enclosing I. But that's not quite it, because you see, because I'm wrapping the wire around many, many times, I'm actually enclosing that current many, many times. Okay, so in this case, I'm enclosing 3 segments of that wire, so I'd be enclosing 3I, but there's nothing special about the way I drew this, okay? So instead what I'm going to say is the current I'm enclosing is equal to N times I. It's the number of turns of the wire times the current per turn. Okay, so if I have 1 amp going through the wire, but I'm enclosing 100 turns of wire, I'm actually enclosing a total of 100 amps. Okay? Does that make sense then? So this is how we deal with the I enclosed. And then of course, to finish it all off, we have B dot dl equaling mu naught times I enclosed, giving us the following. B dot dl, that's this part. It's just the B field times the length that we're choosing for that segment right there. That equals mu naught times I enclosed, which is N times I. It's just the number of turns times the current in each turn. That means our B is this. It's mu naught, divide out the L like this. I'll just write N divided by L times I. Now this part right here, that should look familiar. This is the number of turns of wire per unit length in our solenoid. And that's just the definition of lowercase n. Okay, so the number of turns per unit length is lowercase n. So typically the way we write this is mu naught times lowercase n times I. So basically, it just depends on 2 factors. It depends on how much current you're running through the wire, but also how tightly you wind it. The more tightly you wind the wire, the greater this number, lowercase n, is going to be. Okay? So, any questions on that? So that's how it works for a solenoid. They're all actually the same. You know, it all works out this way when you see a solenoid. So, if you're all good on that, let's summarize. And to summarize, we applied Ampere's law to this rectangular loop, where we said it has dimensions length and width. But those dimensions turned out didn't really matter, because we ended up with this expression, which is mu naught times lowercase n times I. Okay? So, with that said, let's do an example. We have this result. And what I'm going to ask you is, how can we design a solenoid that gives us a certain magnetic field strength? Okay? So you want to design a solenoid that produces 1.5 10 to the minus 3 Tesla of magnetic field on its interior when you have 2.5 amps of current that's running through the wire. Okay? The solenoid is filled with empty space, so that mu naught has 4 pi 10 to the minus 7 as its value right here. How many turns of wire per meter will be required? That's lowercase n. Okay, so that's just a straight plug and chug. Now, the follow-up question is this. If the neighboring turns of wire are touching each other, so it's packed as tightly as you can get. Okay, there's not like space between the turns of wire, they're just all touching. If that's the case, what diameter of wire should be used? Okay? This is also known as like the gauge of the wire. So work out the first part, and hopefully once you've worked that out, you'll see how the second part goes. Take a few minutes, and then we'll go through it together. Any idea how to do the second part? Think about this. If that's how many turns per meter there are, think about how many meters per turn there are. So each turn of wire takes up a certain distance. That would actually be very handy. Okay, so I see a lot of you got the first part already. Someone want to tell me how many turns of wire per meter are required here?
477.
About 477, right? So that part is pretty straightforward because we're just taking our result. B, the magnetic field inside the solenoid, is mu naught Ni. And we're solving for N, which represents the number of turns per meter. So we have B divided by mu naught I. Plugging in the numbers, we want our magnetic field strength to be 1.5 millitesla, 10 to the minus 3 Tesla. Mu naught is 4 pi, 10 to the minus 7, and the units are Tesla times meters per amp. And then our current, we're saying, is 2.5 amps. So it's not a crazy amount of current, easily achievable, right? And that's where you get, we just keep an extra decimal place, 477.46-ish inverse meters. If you take a look at the units, Tesla cancel, amperes cancel, we just have inverse meters. Okay, go ahead. What's that?
A fraction of a turn?
No. Well, we'll hear it. I mean, ideally, you're going to sort of have the wires starting and ending at the same place on your cylinder, in which case you'll have complete turns. But yeah, there's no reason you can't like have a, the last turn be partial, right? Or like only wrapped around halfway. So anyway, this, if we round to the nearest number of complete turns, it's 477. So if we had a meter-long solenoid, we would need 477 wrappings of the wire for this to work, okay? Now, on the other hand, for the diameter of the wire, it actually turns out it's just the inverse of this answer, okay? Because if you think about it, let's draw each turn of wire with no space in between. Again, they're touching one another, right? So if this is how many turns of wire per meter there are, we could ask the question, how many meters are there per turn of wire, okay? So in other words, this is like N divided by L. We want L divided by N. So let's take 1 over 477.46 inverse meters. And can someone tell me what that works out to right there? 0.00209 meters. And then this is, of course, per turn. Okay? So what that's telling us is each turn of wire takes up a length along the solenoid of 2.09 millimeters. Okay? And if they're all touching each other, that means the diameter is actually 2.09 millimeters because there's no space in between. Okay? That makes sense, everybody? So let's do the next example, which is the toroid. Okay? So we've done straight wires, we've done solenoids, next one is the toroid. So this one, you know, unlike the straight wire example where we have a lot of different variations on it, with the solenoid and the toroid, you just need to see it once and that's pretty much how it works across the board, okay? So let me just remind you what a toroid is. A toroid is a donut-shaped object with a wire that carries a current wrapped around that shape many, many times. And one way you can think about a toroid is you can think about it as a solenoid where we bend that solenoid into a circle and connect it back on itself. Does that make sense? Because a solenoid is just a cylinder with a bunch of wrappings of wire. So if we're to bend that into a donut shape and connect it back to itself, we'd essentially have a toroid, okay? So here's how we're going to use Ampere's law to analyze the toroid. So just like before, we're going to take a cross-section of the toroid, okay? So imagine we take a slice of it, like imagine you have like a donut or bagel shape and you slice it in half. That's the cross-section we're looking at right here. So for the segments of wire that are on the outer edge of that toroid, all of those will be carrying a current going in a certain direction. Whereas on the other side, we'll see the current going the other way, right? Because it's looped around. So for example, current's coming out, loops around, and then it's going in over here, right? Then it loops back around, it's coming out, now it's going in over here. That's the picture. The B field, I'm going to just tell you what it looks like. The B field basically forms circular loops around the toroid. So much like with the solenoid, the B field on the inside is fairly uniform and strong, whereas on the outside, the B field can be treated as if it's essentially zero, okay? So here's what we're going to use for this case. We're going to take an Amporian loop, which basically goes around the toroid exactly how the B field is going in a circular path, okay? So the radius of that circular path, we're going to use lowercase r to denote that, all right? So let me ask you this. If there are n turns of wire in total going around the toroid, and the amount of current that's running through those wire segments is I, how should we think about the total enclosed current in this case? So I'm only showing you part of it, right? Just imagine this goes all the way around, it connects back up, right? How should I think about the total current that we're enclosing? Was it?
The current density?
Well, we're not really dealing with that. We're just dealing with current going through small, thin wires. So instead, here's how you want to think about it, right? This Amporian loop, it's enclosing every bit of current on the inside of the toroid, right? But it's not enclosing this stuff on the outside, right? So basically, if each one of these segments of wire, if each one of these turns of wire carries current I, and we have n of those, then the total current I'm enclosing is n times I. So for example, remember if we have 1 amp going through the wire, but it's wrapped around 1,000 times, I'm effectively enclosing 1,000 amps. Okay, so it's really the same idea as before. All right. Okay, so with that said, we can work out the result. So now we're doing the toroid. So for the toroid, we have the following. We have I enclosed is equal to big N. That's the number of times in total that the wire is wrapped around the toroid, times I. That's the current that's running through the wire. Okay? Now, for the other part of Ampere's law, we have V dot dl integrated over our loop. Now this loop is not in any way similar to that of the solenoid. It's actually a lot more like for a straight wire, right? Because our loop goes in a full circle all the way around, following the B field the entire time, right? So in other words, I'll just sketch it out for you. Our B field just kind of loops around the toroid like this in a circle, and the path we're taking just exactly follows that loop, okay? So how should I think about B dot dl? That's B, whatever the B field strength is, times dl, times cosine of what? Cosine 0, because we've constructed our path so that it's just pointing in the same direction as the B field at all times, okay? That's the idea. So there's 0 degrees between them. All right, next, I'm going to use a fact that we've used in the past, right? See, the strength of this B field we expect only depends on your distance r, okay? And if we're going in a circle at a fixed radius r, we should have a fixed B field strength. In other words, B is a constant that we can pull out. That's always got to be the case for us to use this, okay? So now we have B times the integral dl around the path. Now this is just the total distance that you go around the circle, right? So what would that be as an expression?
2 pi r.
That would be 2 pi r, right? Because we're going around a full circle. So we have B times 2 pi r, okay? That's really going to be the case whenever you have a B field that has circular loops, and you just follow one of those loops, okay? So now we apply Ampere's law, which says B dot dl equals mu naught times I enclosed, and plug in what we have. So we have B times 2 pi r equals mu naught times N times I. That's what we have. So if we solve for B, we get the following. We get mu naught N times I divided by 2 pi r. And that's it. Okay, so that's the B field from the toroid. What does it depend on? How many turns of wire we have, how many times we choose to wrap the wire around the toroid, how much current that we choose to run through the wire, but also the radius. That ends up mattering here, okay? So any questions on this one? If not, we're going to take a look at one last case. That last case is a plane of charge, okay? So what have we knocked out for Ampere's law? Straight wires, solenoids, toroids. Okay? The last one is a sheet of charge, or a plane of charge. Or, a sheet of current. Not a sheet of charge. A sheet of current. Yeah. Okay, so there's our result. And now you know how it's derived. Okay. So let's do the infinite current sheet next. So the way I'm going to present this to you is like this, okay? What you want to imagine, of course, is a two-dimensional sheet which has current running across it in just one direction, okay? So it's not like the current is flowing in a complex way across the sheet, it's just uniformly flowing in one direction across the sheet. We'll also imagine, it actually makes it simpler to imagine, that the sheet is infinite in its extent, okay? So one way we can create a sheet like this is to put a bunch of wires parallel to each other along the sheet. So I have a wire going like this, right next to it, another wire going like this with current going the same way. Just line them all up. The wires are infinitely long. You spread them out infinitely far this way. Now you've got an infinite current sheet. So that's how you can imagine constructing this sort of thing. Okay, so what do we have? We have many parallel wires packed tightly together. They all carry the same amount of current going in the same direction. Let's let lowercase n represent the number of turns we have, the number of wires we have per unit length, okay? So like if I have 1,000 of these for every meter, then it would be, 1,000 inverse meters, that kind of thing. Can anyone get a sense of what the B field should look like for an infinite current sheet? What I want you to do is this. I want you to use the right hand rule, okay? Every single one of these wires, if we look at it individually, creates a B field that actually loops around the wire, right? But we have a whole bunch of those and we have to imagine how they add together, okay? So let's just look at one to start, right? Let's say this guy. I'm going to point my thumb out of the page in the direction that the current is going. And I'm going to do this with my right hand, because if I do it with my left hand, I get the wrong answer, right? And you see my fingers are curling this way, right? So they're curling in a counterclockwise fashion, right? Right, so that means up here, okay, right above that wire, my field is going to the left. You see that? But then right below it, it's going the other way, okay? So what I'm going to show you, and then I'll expand on this a little bit more, is that right on top of the sheet, we have a uniform B field going one way, and right on the bottom of the sheet, we have a uniform B field going the other way, okay? Does that make sense just based on the way the right-hand rule works? Okay. So the next thing we want to do, everybody, is choose our Amporian loop, all right? So we're going to apply Ampere's law to solve for the B field, how strong it is. And in order to do that, we need to choose some kind of Amporian loop. I'll give you a hint. We're going to choose the same loop that we've used in a previous case. Any guess which one that is? Yeah, this case is quite similar to the solenoid in how we want to think about the Amporian loop. So we'll use the same idea. We'll use a rectangle where that rectangle goes through the B field both on the top and the bottom. But unlike in the case of the solenoid, the B field is present in both the top and the bottom, okay? So that's where it's a little bit different. So here is our loop. We start with path number 1. With path number 1, we're going to just go straight along the B field lines on the top, like this. Path number 2, we're going to go perpendicular to the B field lines like this to go from one side of the sheet to the other. Path number 3, we're going to cut across the B field going with it, but on the bottom of the sheet. And then path number 4, we're going to cut across perpendicular to the B field, just like that. So can anyone tell me, when we integrate B.dl around the loop, breaking it up into these 4 segments, which of these segments are going to give us 0 for that integral?
2 and 4.
It's going to be 2 and 4, right? Because remember, dl is a little piece of this path, right? Let's look at number 2 as an example. My dl vector for number 2 would be going straight up, whereas my B field would be going straight to the right or straight to the left. Either way, it's at a right angle, right? If you do B.dl and those 2 vectors are at a right angle, you're automatically getting 0, okay? And it's the same case for number 4. So really, it's just 1 and 3 that we have to think about in any kind of detail, okay? So let's focus now our attention on those 2 parts and work out the result. Okay. So I'll start by sketching out what we have. We have So in this case, we're imagining the current's coming out at us. So I'll show a bunch of those wires coming out like this. And then I'll draw that rectangular path once again. Okay, so remember, on the top, we had the B field going straight to the left like this. And on the bottom, we had the B field going straight to the right like this. And it's perfectly symmetrical on the top and bottom, right? Whatever B field we have up here, we should expect to have the same amount of B field down here, okay? So with that said, let me just remember how I labeled these. We had 1, 2, 3, and 4 like this, okay? So if I take the integral of b dot dl around the entire closed path, remember that's going to be path 1, b dot dl, and then the same for path 2, and then path 3, and then path 4 all added together. All right? But you guys already determined that 2 and 4 are both going to be 0, and the reason is B is perpendicular to DL. Okay? So that's the reason why. So let's work out the others. Okay? For B dot DL1, here's what we have. We have the integral of B times DL1. That's just a little piece of this path. That's what DL1 means. And then we take cosine of what angle in evaluating the dot product?
Cosine.
Cosine of
0.
0, yeah. Because your B and your DL go in the same exact direction. That's the way we constructed this, right? Okay, then we have the same thing for path number 3. We have B, DL3, cosine, what angle for path 3? Also 0. It's still going exactly along the B field, right? So for both of these, cosine 0 picks up a factor of 1, which we don't really have to write, okay? Okay, so next. I'm going to take B, pull it out of this integral, and then we have DL1 left inside the integral. And then for this one, I have B, pull that out of the integral, and then I have DL3 left inside. And keep in mind, again, there's symmetry between the top and bottom. We expect the same B field on the top and bottom. There's no difference between those two situations, right? So, okay. Let's just call this length right here L. It's the same length, by the way, for 1 and 3. It's just the length of this particular side of our rectangle, okay? So for number 1, I just have B times whatever that length is. That's what I get when I add up all the little bits along the path. And then same for this guy. It's B times L. So overall, it's 2B times L. So it's like what we had with the solenoid, but times 2, because we don't have 0 B field on one side. We have a B field on both sides, okay? So the next thing I'll do is this. I enclosed, right? Remember, whenever we use Ampere's law, a good strategy to use is to work out the I enclosed part of the equation, and then the B dot DL part, and then put them together at the end. So for I enclosed, I think we've seen how to do this before, right? I'm enclosing some number of wires, right? Maybe I'm enclosing 20 of them, right? So that number of wires, we'll call it N, times the current that each one is has running through it. That gives me the total current that I'm enclosing, okay? So that's pretty familiar from the last couple examples, right? So what do we get when we put it all together? We take B dot DL equals mu naught times I enclosed. We get the following. We get 2BL, that's the result of the integral, and then we get mu naught times N times I right here. And then I solve for B. That's going to give me 1/2, because I'm going to divide out this 2 factor. I'm going to divide out this L factor, and I'll put it as N divided by L like this, times I. So remember, N divided by L, the number of segments of wire per unit length that we have. We tend to call that lowercase n. So I'm just going to make that substitution right here. So we have 1/2 mu naught times lowercase n times I. So that's the result if we have an infinite current sheet. Okay? So any questions on this one? In a lot of ways, it's similar to the solenoid and how we analyzed it, right? Okay, so if there are no questions, I'll give you the summary. In this case, we have 1/2 mu naught times lowercase n times I, where this is the number of wires per unit length. That's what lowercase n means. All right, so that is Ampere's law. Okay, you've seen all the different types of geometries that you should know. Again, current sheets, toroids, solenoids. Those 3 are, maybe tricky the first time you see them, but there's really only one example, right? And then you have straight wires. In that case, we've seen a lot of different examples that fall under the straight wires category, okay? So now, we're going to look at something called the Biot-Savart law. And what this is basically a different way, another way of calculating B fields. Okay, we've seen how to use Ampere's law to calculate a B field, and now we have something called the Biot-Savart law. And I want you to look at these 2 side by side, all right? This is actually the Biot-Savart law. We're going to go through this in a second, so don't feel the need to jot this down quite yet. But I just want you to compare it to something we've actually already seen, okay? Which is when we calculate E fields, electric fields, we had 2 ways of doing it, right? We had Gauss's law, and then we also had Coulomb's law, right? Remember these 2 methods for calculating an E field? So how do they kind of compare to each other? Let's take a look at Coulomb's law. That says dE is equal to K times dQ divided by R squared, where the idea here is you take whatever distribution of charge you have, you break it into little infinitesimal elements, which we call dQ. And then when you integrate over all of your dQs, then you can get the total E field. That's how that sort of situation was going. Now, when it came to Gauss's law, we had integral over a closed surface, E dot dA equals Q enclosed divided by epsilon naught. So remember, for Gauss's law, we were really only able to use it when we had certain types of symmetry. Remember, we had spherical symmetry, we had cylindrical symmetry, and planar symmetry. And it was really only good for those situations. Whereas this could be used in a lot of other situations where you don't have a nice symmetry, okay? So what we say is Coulomb's law is kind of like the brute force approach. Gets kind of messy, but you can just kind of work it out via brute force. This is kind of a more elegant way to do it, but it's only useful in certain situations. It's exactly the same when we calculate B fields using Ampere's law versus the Biot-Savart law. So Ampere's law is a lot like Gauss's law. All right, it's a nice clean way to do the calculation, but you can only use it if you have a certain type of symmetry. Remember, a sheet of current, toroids, solenoids, and long straight wires, right? Pretty much if we're dealing with that kind of symmetry, we can use Ampere's law. If we do not have a nice symmetry, now we have to use this thing, the Biot-Savart law, okay? It's a lot like Coulomb's law in that it's a brute force integration method. You take some current, you break it into little pieces, infinitesimal elements of current. You integrate over those elements to get the total B field. That's how it goes, okay? So with that said, let me introduce you to the Biot-Savart law. So, the Biot-Savart law describes a magnetic field created by an infinitesimal piece of current at some point in space. Okay? So, a general picture that will work well enough to do pretty much any problem is this. Imagine you have a wire. It can be bent into any kind of crazy shape. It doesn't have to have a nice symmetry to it. Just any kind of wire. It carries a current going through it. That current is I. Now what we want to do here is locate a current element. We don't want to look at the whole wire altogether. Instead, we want to take a little piece of it and call this our current element. Okay? So our current element is given by dl. All right? dl is a vector. Which way is it pointing? It's pointing in the direction that your current is flowing. That's pretty straightforward. What's the magnitude of it? It's just however long that current element is. Okay? So it has a direction. It's in the direction your current is flowing. That's your conventional current, by the way. And it's just however long that little segment is. Okay? That's your magnitude. All right. So that's our current element. But this over here is what I'm labeling as point P. These are two different things, right? This is where the current is located, and this is where we're trying to calculate the B field. So I want to know what the B field is at this point P. Okay, that's what we might call our field point. Okay? So there's a distance between the two, right? There's a distance between my current element and my field point. What we call that distance is R. Okay? The distance between the current element and your field point is R. But we can also think about R like a vector, right? Because I could take an arrow, start here, where my current element is located, and end up over here at that point P. So R as a vector is going from the current element to point P. Okay, just an arrow straight across. Okay, R hat, this is also going to come into the equation. You guys remember what it means to put a little hat on top of a vector?
Unit vector, right?
It's a unit vector. So R hat, this is important to keep in mind, is a unit vector going in this direction. Okay? So in general, of course, this can have any length that you want. But when we take R hat, it becomes a unit vector. It's still pointing this way, okay? But it's a unit vector, which means it has length 1. Okay? So those are all the things that go into the formula. So here's the formula then. dB, that's the field just contributed by this little piece. So it's an infinitesimal. We call it dB. It's equal to mu naught times I times dl, that's this guy, crossed with R hat, that's this unit vector, divided by 4 pi r squared. Okay? So that's how we set up the infinitesimal element. But then we have to integrate over the entire wire, basically, to get the entire field. Okay? So that's how this works. Gets a little tricky, so I'm going to show you some examples. Okay? But before we do that, do we have just any questions about what the variables mean? Just want to make sure we all understand the variables. Okay, so let's get into our first example. In this first example, we're going to look at an infinitely long thin wire. Now actually, we kind of know what the answer should be, right? This is one of the very first things we did in this lecture. So we kind of have an expectation that it's going to be mu naught I divided by 2 pi times distance. Okay, that's the result we expect. But we're going to do it using this brute force method of the Biot-Savart law. So here is our infinitely long wire. It extends infinitely far up and infinitely far down. Let's suppose that the current is going up. Okay? And what we want to do is calculate the field due to this wire at this point in space right here. Let's call the distance d. So the kind of perpendicular distance from the wire to our field point is d. Okay, so we need to make a very detailed diagram in order to be able to work this out. So let's start by choosing our current element. We're gonna choose a DL to kind of construct the integral, and then we'll just integrate over all the DLs to get the answer, okay? But remember, DL, it points in a certain direction, right? It points in the direction that current is flowing. So if current is flowing up, the DL vector is pointing straight up, okay? It has some tiny little thickness along the y-axis here, okay? Okay, next. Let's draw the R vector. You see the R vector goes from your current element, which is here, to your field point, which is here. So that's the R vector. Remember, if I refer to R hat, that's the same vector, but with length 1. It's pointing this way, but with length 1. Okay? All right, so right away, if you look at the Biot-Savart law, there's a cross product inside it, right? So we can use that cross product to figure out what the direction of our B field is, okay? So DL, this vector, crossed with R hat, which is going this way, right? So you guys tell me, what direction is that cross product going? Should be going into the page, right? You do DL, point your fingers on your right hand straight up, and then curl this way. Your thumb goes into the page. So the B field here is going into the page. And the nice thing about this one, at least, is that it doesn't matter which part of the wire you pick out, you're always going to see that DB is going into the page. So when we add up all the contributions from all the different current elements, we don't have to really worry about the vectors. They're all going into the page. Okay? So now that we figured out that every DB is going into the page from the right-hand rule, let's figure out the magnitude of DB, okay? So let me explain how I went from here to here, okay? The magnitude of DB is basically taking this formula for the Biot-Savart law that we started with, but just instead of taking the cross product, evaluating the magnitude of the cross product, okay? Remember how this works. If we have a cross product, we take magnitude of the first vector times magnitude of the second vector times sine of the angle between the two vectors. That's how we evaluate a cross product. So notice I have mu naught times I divided by 4 pi r squared. I'm just leaving that as is. For the DL cross r hat, here's what I have. Evaluating the magnitude gives me magnitude DL. R hat, that's a unit vector. Just by definition, that has a magnitude of 1, okay? That's why I'm putting a 1 in right there. Does that make sense? A unit vector has a magnitude of 1. That's the definition. And then I have sine of theta, where theta is the angle between these two right here. I'm not able to put a actual number to theta, by the way, because it depends on which part of the line we're on. Like, if I'm right here, theta would be 90, but if I'm down here, it would be something smaller. So we just have to call it theta and try to sub it out at some point. Okay, so moving on from there. What I'm going to attempt to do is set up this integral so that at the end of the day, we're integrating over the y-axis from minus infinity, which is all the way down there, to positive infinity, which is all the way up here. So what I'm attempting to do is rewriting everything in this integral in terms of y, okay? And we'll start with dl. So dl is just some piece of this overall wire, and I can write that as dy, some sort of distance along the y-axis that it spans, okay? The next thing I'll do, maybe you guys can tell me, how can I write r, the distance between the point and the current element in terms of the variables we have here? So if I wanted to know this distance, looks like I have a right triangle, I can do that, right? Pythagorean theorem, that's right. So check it out. I'm going to call this distance from this line to where the element is located y. Okay, so y just locates how far down you have to go to get to the current element. And if I take y squared plus d squared, this distance squared plus this distance squared, under the radical, that gives me r. Okay? Does that make sense? What about sine of theta? Again, I don't want that floating around. I want to express this in terms of my variable y. So how would I do that? What's the definition of sine if we have a right triangle? Opposite over hypotenuse, right? That would be d divided by r. That'd be sine theta, d divided by r, right? Just using the definition of sine. But here's the thing, I don't like r. I want to re-express that as d divided by the square root d squared plus y squared, okay? So is that all making sense? All right, again, it's a little tricky, but those are the ingredients that are going into it. So what I'm going to do is plug in all of those substitutions. Let's be clear, I'm starting right here, and I'm making all the substitutions we just outlined to get to this line. So we have mu naught times I divided by 4 pi. That part is the same as before. But my r squared, I'm now writing that as square root d squared plus y squared, square that, okay? Then I have the length of my element, which now we're calling dy, okay? And then I have sine of theta, which I'm now expressing as d divided by the square root of d squared plus y squared, okay? So can any of that be simplified?
Yeah.
Looks like we have a lot of different factors of root d squared plus y squared. So how can I consolidate that into one thing? 3/2 power, that's right. And I'm also going to, in another step, separate out what's constant from what isn't, okay? Mu naught times I times d divided by 4 pi, that's all a bunch of constants in the front. Then we have dy on top, and then d squared plus y squared to the 3/2 power on the bottom. So now we've pretty much done what we've set out to do in terms of setting the integral up, okay? We want to be able to write this in terms of just a single variable that we can integrate over. In this case, y, right? So now all I have to do is put this inside of an integral and go between what limits for y again? What's my bottom limit? Negative infinity. What's my top limit? That's right. Okay, so that's what we have for dB. All right, same thing I showed you earlier. And now it's time to integrate over all of my dBs to get the total B field. So this should be looking familiar because we did similar things with Coulomb's law. Remember we had dE and we wanted to integrate over all of those to get the total E field. Same idea here, okay? So I've already identified what the constants are, so let's immediately pull them out. Mu naught times I times d divided by 4 pi. Then we have the integral going from minus infinity to positive infinity of dy divided by d squared plus y squared 3/2 power. All right? So I'm going to just tell you what this integral works out to. You do need to do a trig sub sort of thing to work it all out. We don't have enough time to go through that today, but we have seen things like this in the past. Okay, so I'll let you refer back to your notes from actually the first chapter we did. We did some trig sub integrals there. And the result is this works out to 2 divided by d squared. Okay? If you want, you can plug that into Wolfram alpha and verify it works out to 2 divided by d squared. Okay? So that integral works out to 2 divided by d squared. We have mu naught I times d divided by 4 pi times 2 divided by d squared. So we get some cancellation here, right? Overall, just a factor of 2 on the bottom. How many factors of D are we dealing with? Just 1 factor on the bottom, right? We cross cancel here. So the result is u naught I divided by 2 pi d. And remember, we have obtained this result already using Ampere's law. So, I mean, you tell me, what was easier, to get this result using Ampere's law or doing it this way?
Amperian Loop.
Probably, right? So when you can use Ampere's law, I would suggest you use it. But the problem is you can't always use it, in which case the brute force method is the only way to go. Okay? All right. So any questions on this example? We're going to go through some more. All right. So next, I'm going to ask you kind of a conceptual question. You don't really need to go through a complicated calculation. You just need to draw a picture to see how this one works out. But basically, what we have is a circular loop of current with radius r. Okay? We want to figure out what the B field from a circular loop of current is. Okay? So you can imagine a wire bent into a circle, and current I is just flowing around the circle like this. That's all that's going on. Now, let's put the circle in the xy plane with the center right at the origin. And let's say that we want to calculate the field at this point P, which is up here on the z-axis somewhere. Okay? So what you're going to see here is, if you make a little sketch, some of the components of B will turn out to be 0, right? We think there might be an x component, there might be a y component, and then a z component potentially. Some of those components, I'm telling you, will be 0, okay? Which ones will be 0? Make an argument from symmetry.
X and Y.
Okay, yeah, but draw the picture. Even if you've got it in your head, just draw it, and you'll have 2 current elements on opposite sides of the loop. See how their components cancel. Yeah. So you do have the answer, but draw it up. Okay.
Would that behave like a super weak solenoid?
So the thing about a solenoid is, in order for any of the equations we derived to be valid, you have to assume that its length is very big compared to its diameter. And that's definitely not the case here. So in your picture, you should have a DL vector on each side of the loop. Okay. It might be helpful just to draw the picture like as viewed from the side, so you're seeing the loop like edge on. That might be easier to visualize. Exactly. And then so what, but again, try drawing the DL. Try to draw the little current elements that are actually on the loop. Okay, so let's go through this one together real quick, all right? So what I want you to try is drawing the picture as viewed from the side. So the loop of current, oops, ran out of ink. Hold on a sec. So yeah, the loop of current, we're seeing it edge on like this. And the z-axis is going straight up like this from our point of view. And then this is our field point, okay? I'm actually going to write down the Biot-Savart law on the side, because this will give us a sense of what sorts of vectors we want to draw on the diagram. We're going to have u naught times I times dl crossed with r hat and we're going to divide all that by 4 pi r squared. That's just the VO law. So in particular, I'm interested in dl and r hat. So I want to take a little bit of current on each side of the loop, on opposite sides. Let's say that my first dl vector is on this side, and the current is coming out of the page on this side. So my dl vector itself, I'll label this one dl1, is coming out of the page, right? So the idea is it's looping around, so on this side it's coming out of the page, on this side it's going into the page for current, okay? So what should my R vector look like? That's going to be going from this current element to the field point like this. So next I'll draw the vector R hat, but I'll label it as R hat 1, okay? So if we want to figure out what dB is, what is the magnetic field contributed by this little bit of current, we need to do dl crossed with r hat, okay? So it's a little tricky, but you've got to start with your right hand pointing out of the page like this. And then you have to curl like this, and your thumb ends up pointing kind of like up and to the left when you do that. You see that? So dl cross r hat. And remember, when you cross two vectors, it's perpendicular to both. So I know that the B field is perpendicular to this line right here. That's my dV1. Okay, so that's the picture I wanted you to draw. Next, let's do the opposite side of the loop, where the dl vector is going into the page. Call that dl2. Okay, let's draw a line to our field point. This is our vector R, R2 hat like this, okay? And again, we're going to take the dl vector cross with the R hat vector. So I'm going to point my fingers into the page for dl, cross like this for R hat, and then I'm kind of going up and to the right like this, but I know that I'm also perpendicular to this line. So this is the drawing I wanted you guys to make right here. But from that drawing, it should be clear that everything except for z components is going to cancel out. Okay? Anything that's not just pointing up along the z-axis is going to cancel in pairs. Okay? So because of the symmetry, we have bx and by both equaling 0. It's only z that is non-zero in this case. Okay? Y'all see that?
Could you do the right-hand rule for dV2 one more time?
Yeah. So remember, if we're on two opposite sides of the loop, the current will be going in opposite directions. So this one is going into the page, right? So right hand's going into the page, and then curl like this. There's dV.
Thank you.
Okay, so with that, we figured out the results. So now we know that in this case, we only have a z component, right? Let's calculate what that z component actually is, okay? So let's calculate how strong the B field is at this point on the z-axis, okay? So here are some variables that are going to go into it. R, capital R, is the radius of the loop itself, and z is going to be how high from the center of the loop to that point P do we have to go, okay? And then of course we have the current I. Those are some of the numbers that are going to go into our formula. All right, let's work it out. So I'm going to use a very similar kind of picture to what we drew here. Pretty much the same thing, but I want to put more labels on it, so let's just start fresh. We're still viewing the loop from the side just like before. Now this time, I don't really need to make a symmetry argument, so I'm just going to show one of my DLs and then the dB that it creates and go from there. So I could pick anything, but let's just try this one, the one on the side. Let's say the current is going into the page on this side of the loop. So my DL vector is going into the page. This is our z-axis. This is the point on the z-axis where we're trying to calculate the field. And right there is the vector r going from DL to the point. But when we say r hat, we're talking about the unit vector with length of 1. Okay? As we determined before, the B field is going to point somewhat like this, like up and to the right. It's going to make a right angle with this line. Okay, so the next thing to see is that we only care about z components, right? We know that x and y components are just going to 0. So I'm going to specifically pick out the z component right here. So right here, if I project my dB vector onto the z-axis, this is going to be dB subscript z component, okay? In order to get that component, it might be helpful to know what this angle right here is. So I'll call that angle phi. And I want you to notice something. That same angle phi appears down here, okay? So these are equivalent angles, okay? So next, I'm going to label some distances. This distance is z, so going from basically the origin to our point. This long side is lowercase r, okay? And then this side down here is uppercase r, because that's the radius of the loop. If I go from the center to the edge, that's the radius of the loop, okay? So that's a right triangle where we have those side lengths. So does this picture make sense to everybody? Do you have any questions so far? Okay, so let's do this. If I'm trying to find dBz, just the z component of my vector dB, that's going to be the magnitude of my vector times cosine of the angle phi, because it's the adjacent side in this top triangle. So if I take the cosine of phi, I pick out the z component, okay? All right. Next, let's write down, well, what is the magnitude of my vector dB in the first place? And for that, I'm going to remind you of what the Biot-Savart law says. It's mu naught I dl crossed with r hat divided by 4 pi r squared. That's what it is. If I want the magnitude, here's what that's going to give me. I'll just write all the scalar stuff. Mu naught times I divided by 4 pi r squared in the front. And then I have dl crossed with r hat. So basically, if I'm finding the magnitude, I'm trying to take the magnitude of dl cross r hat, okay? Just to say explicitly what I'm doing. So let's take that same set of constants out front and then evaluate the cross product dl cross r hat. Well, that's going to be magnitude of the first vector, which I'm just for now going to label as dl, times the magnitude of the second vector. What's the magnitude of r hat? 1. That's 1. Okay, whenever you use the Biot-Savart law, r hat is a unit vector. By definition, it has magnitude 1. And then we take the sine of the angle between dl and r hat. What is the angle between dl and r hat?
90, no?
It's 90. It has nothing to do with this angle phi. dl is going this way. R hat is going this way. One of them is on the page. The other is perpendicular to the page. They're at a right angle, okay? Everyone see that? That's a 90-degree angle, which is actually just another factor of 1. So that's pretty easy to deal with, right? Okay, so here's what we have then. dBz is this magnitude, which is mu naught I divided by 4 pi r squared times dl. And then both of these are 1, okay? But then I have this cosine phi factor, which came from taking the z component. Okay, so that's dBz right there. Okay? So here's what we'll do next. Make some substitutions. Okay, lowercase r, which again is the distance between my point and my current element. How can I write that given the right triangle on the bottom?
Square root of z squared plus r squared, big R squared.
This is square root z squared plus big R squared. Okay, what about cosine of phi? There's another thing we can sub out in terms of the right triangle variables. What do we have? We have,
Big R over the square root of z squared plus big R squared.
yeah, so it's the adjacent side divided by the hypotenuse. So that's big R divided by little r, which is big R divided by square root z squared plus big R squared. That's right. And put all that into here. I have mu naught times I divided by 4 pi. Take the square root of z squared plus big R squared. But then I'll square that whole thing, right? That's little r squared. And then I'll have dl. And then I'll have cosine phi, which I'll replace with big R divided by the square root of big R squared plus z squared. So, I mean, these are the same thing, right? So overall, when we collect our factors, how can I simplify this guy? Same as before, actually. So if I have square root and 3 powers of that, that's the 3/2 power, remember? So I have mu naught times I times big R, divide out 4 pi, and then when I consolidate all of those factors, it's z squared plus big R squared to the power of 3/2, and then dl. Here's the really nice thing about this one. All of that stuff out there is constant, right? Let's think about it. I mean, current, the radius of our ring, big R is a constant, and so is z. That's just how high up on the z-axis is our point, okay? So all of that's constant, and then we have dl. So it looks like if I want to calculate the total field, keeping in mind that I'm only really interested in the z component because the other components are 0, that says bz is the integral of dbz over all of the current elements. So it's an integral. We immediately know what the constants are, which we can pull out. That's mu naught I times capital R divided by 4 pi times z squared plus r squared to the 3/2 power. And then we have integral dl. All right, let's think about it. dl is a little bit of distance along the loop. When we integrate over all of those dl's, we get the total distance around the loop. What is that? Yep. That's 2 pi r, distance around the loop. Okay, so when I put that 2 pi on top, I cancel out this factor of pi, and I end up with a factor of 2 on the bottom. This r combines with this factor of r to give me an r squared. So if I put it all together, here's what I have. I have mu naught times I times r squared divided by 2 z squared plus r squared to the power of 3/2. Okay? That's the answer. And we're actually going to stay a little bit on this problem in the next lecture because we want to see how this behaves in the far field limit when you get really far away from the loop. Does this simplify to something? So we'll do that in the next lecture, and we'll finish this entire chapter up in the next lecture, which is going to be pre-recorded. So I'll see you then.